Last time we were looking at an atom that starts out in an excited state and makes a transition to a lower energy state, emitting a single photon. So, and we were looking at it in the dipole approximation. So radiated emission, well, let's say emission, atomic emission of a single photon and we have our atom here, and it's emitting a photon with a wave vector k and a polarization r, and we were looking at it in the dipole, the electric dipole. Approximation with an interaction Hamiltonian given by this term here. It's minus the dot product of the electric dipole moment with the electric field evaluated at the origin. So, and we found the following result, that the, so let me see. So the transition probability, we calculated the transition probability per second or per unit time per second into d omega. So we're thinking of a solid angle element, d omega. You can imagine if you have a detector with a small area that is detecting the photon. So the transition probability per second into a solid angle element, d omega, is given by, so we found the following result. WR d omega equals E squared omega AB cubed d omega divided by 8 pi squared h bar c cubed nkr plus 1 mod epsilon kr dot x va squared, where omega AB is equal to dA minus dB over h bar. So the atom is making a transition from an initial state A to a lower state B and is emitting a photon. Okay, symbolically, starting in an upper energy state, falling to a lower energy state, emitting a photon. So this is the frequency of the emitted photon from energy conservation. And let's see, this is the number of photons initially present in the mode KR. XBA is equal to the matrix element between the two atomic states of this quantity X, which is just B times the sum of the position operators of the atomic electrons. All right, so if you were given the wave functions of the atomic states A and B. If you were given the wave functions of the atomic states A and B, you can work out this matrix element. And so you know this quantity, there you are. That is the result. So that's where we were last time. So let's see a couple of features. As I noted, that here the so stimulated emission probability of the emission is increased if there are already photons in that mode. So if the atom is excited and there are already photons present in the NKR mode, the transition probability per second to emit a photon in that mode is bigger. It's proportional. Well, it's n plus 1, but anyway, it is bigger. There is also spontaneous emission. Spontaneous emission, even for NKR is 0. So if there are no photons present initially, so I have an atom in the vacuum that's excited, there are no photons present, the atom can still emit and fall to a lower state and emit a photon. All right, so briefly, some consequences if you wanted to work out the this is the transition probability per second into d omega for the photon to emit a particular polarization R. If we are if our detector is oblivious to polarization. So we're just detecting a photon. We don't care which polarization state it's in. Then the transition probability per second into d omega is really the sum over R is 1 and 2. That is the probability that the photon comes in with this polarization plus the probability it comes in with a different polarization. And so what you would have to work out here, so actually actually the book does something, if we assume that NKR is independent of R, and in fact we're going to look at the case e.g. NKR is just 0, then if you do this sum over R, well, the only term here that depends on R is this, we have to work out, we need to work out this sum modulus epsilon kr dot epsilon kr dot into this vector VA. So this is the first time you're meeting polarization sum. You're going to come to know and love summing, the joy of summing over polarizations. So what you do, there's a trick. So there's a trick, is what you do is you note that epsilon k1, epsilon k2, and here we have the unit wave vector, the wave vector divided by its magnitude. These three, for any given k, these three vectors, they form an orthonormal basis. basis. These three vectors, they are orthogonal, they're unit vectors, so I can always write, I can always write the vector xba as some linear combination of these three vectors, and so I'll leave you to just check, make sure this is correct, but what you can do then is the sum that we're interested in, the sum over R is 1 to 2 of epsilon kr dot xba squared can be written like this: xba dot xba star, remember xba can be complex, minus k hat dot xba k hat dot xba. Okay, this is just saying that this term here is going to be the sum of the squares, of the modular squares of the magnitudes of the components. So if I bring that to the other side, that's what it is, the sum of the modular squares of the components. And I can write this as xba dot, all right, let me do it like this, xba star times 1 minus cos squared theta, where we've defined an angle cos theta that would be the modulus of k hat dot xba divided by the modulus of xba, and so I can write this as, so it's a bit squashed, xba squared sine squared theta. So there we have it. So what happens then is that the if I sum, so with that trick, summing over the polarizations, so the total transition, the transition probability per second into d omega summed over the two polarization states is equal to e squared omega ab cubed over h pi squared h bar c cubed d omega times, well, the book has been a bit naughty here. It doesn't, I'm gonna write nk. The book, it writes as if nk depends on r, but it actually assumes it doesn't when it does this sum. So let's assume that this is independent of r. So the sum over r was just in here, and here there is a term. Term xba squared sine squared theta. There we go. So now let's just look at the case of spontaneous emission, where there are no photons in the initial state, and see if we can work out the total probability per second for the transition. So what do we do? So let's look at spontaneous emission. Spontaneous emission. So what do we have? We have simply the total transition probability per second is going to equal the integral. So So I've got my sum here from R is 1 to 2. This was the transition probability per second into d omega. I have to integrate over d omega. So now use the fact that, so here we've got a sine squared theta. So d omega is d cos theta d phi. So I hope you let me just remind you in case you've forgotten, what does this mean? So d cos theta d phi, d cos theta goes from -1 to +1, d phi goes from 0 to 2 pi. And then I will have the sum r is 1 to WR. So of course the integral from 0 to 2 pi of d phi is just 2 pi. The integral, anyway, let me just write down what we really need, the integral of sine squared theta d omega, or if you like, the integral of sine squared theta d cos theta. Sine squared is 1 minus cos squared, blah, blah, blah. This comes out to be 8 pi over 3. And so, da-da, 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 we have the total transition probability per second for the atom to go from the upper energy state to the lower energy state is equal to E squared omega AB cubed divided by 3 pi h bar c cubed times the modulus squared of this matrix element XAB. Just to remind you where XBA, where XBA is equal to BXA. So, that is it. That is the total transition probability per second. The total transition probability per second. So, something to note, that the lifetime of the atomic state, so the mean time it will take for the atom to decay is just tau equals 1 over W total from A to B. So considering just the transition A to B. So if there were other transitions, so strictly speaking, the lifetime, if there were, if the atom starts in an upper state, there will be transition probabilities to this lower state or to the other lower state, or there could be, of course, a number of different lower states that it could fall into. You'd have to calculate the probability for each, and really the actual lifetime, the true lifetime, would be so the lifetime of the state, of the initial state A, would be given by, I would write it, if I write 1 over the lifetime, 1 over the lifetime is going to be the sum over, I've got the total probability per second for the atom to decay from A to a lower state Bn I would have to sum over the different states. So if I've calculated the probability it falls into this state, I add the probability that it falls into the other state, and then I just sum over the probabilities of all the lower states it could fall into, probabilities per second, sorry, and 1 over that gives you the lifetime of the atomic state. There you go. Now you see the power that you have in your hands. You can now calculate the lifetime of an atom. Similarly, actually, for nuclear decays, I think in an appropriate range of wavelengths, X-ray emission, an excited nucleus, the dipole approximation is also good. Anyway, so this is the kind of thing that you can now do. And what is there? There's a quote from the Bible, is it James, letters to St. James, says something like, "But be ye doers of the word, and not hearers only, deceiving your own selves." So, to check that you really understand this, homework problem. Nice, beautiful homework problem. So, here's what you have to do. Homework. I may as well put the quote here. Maybe Murray can tell me if I've got this right. "But be ye doers of the word, and not hearers only, deceiving your own selves." Deceiving your own selves. There we go. So, study the following. Absorption of a single photon. So the idea is that we have, again, the atom at the origin, and a single photon with wave vector k and polarization is coming in. And it's coming in from some, you can think of it as maybe coming in restricted to some solid angle element d omega. And the state, what we do now is the atom is in a state A, NKR, T is not so the initial state makes a transition to a final state, B, with one less photon. So the atom so the A's and the B's are now swapped around. You can think of it like this. The atom is making an upwards transition and it is absorbing a photon. Right? I have an atom in some energy state, a photon comes in, the atom absorbs the photon, the energy level of the atom is raised, and so the number of photons, there are NKR photons present initially in the mode KR. One of them gets absorbed by the atom, and the atom makes an upwards transition. So you want to look at the matrix element. The matrix element B NKR minus 1 of our interaction Hamiltonian sandwiched between these initial and final states, where this is again just minus d hat dot E, where electric field operator is evaluated at the origin. Now, what you should find so please go through it, work out this matrix element, so you should find it's as before, except, so matrix element has a factor square root of nkr instead of the square root of nkr plus 1. The calculation before, you remember the matrix element, there was a factor of root nkr plus 1. You should get root nkr. And the probability per second when you square the matrix element, so you should have nkr instead of nkr plus 1. Instead of nkr plus 1, you should find that it's replaced by nkr, where d omega equals element of solid angle for the incident photon. Again, this definition, but note now, and at note, we have EB is now bigger than EA. It's making a transition for an upper state, and so our frequency omega AB is going to be EB minus EA over H bar. Whereas before it was the other way around. Before it was EA minus EB, now it's EB minus EA. You should get this. Please go through it, and if you can do this problem, you have a chance of passing the midterm exam. If you can't do this problem, you have no hope in hell. Okay, so please, and if you have any problems, you should understand this perfectly. It should be fairly straightforward. If you have any problems, please email me, homework, office hour, anytime. We can, afternoon is preferred, any day. Please email me and we'll arrange an office hour. In case you don't know my email address, there it is, Antony V at Clemson.edu. This is the emergency helpline. There you go. Your emergency helpline. If you have any problem, please, let's meet, discuss it, go through it. You should be able to do this. This is the kind of thing that will come up in the exam. Calculate this, calculate that, show this, this is what you're going to be doing pretty soon. So, good. Actually, a little announcement, something I forgot, I should have mentioned, wanted to mention at the beginning, is about next week. Hang on, before I say that. So, are there any questions about this? Any questions?
So the transition probability for spontaneous transition is like this one that you have written already. For stimulated one, there will be like only one direction, like NKR plus 1, or it can be derived.
So what is happening, the probability for emission is proportional to NKR plus 1. So in other words, it's proportional to the total number of photons present plus 1. And so you can think of this as that there are two contributions to the emission probability. One is due to the fact that there are already photons present in the state. And photons, being bosons, we'll discuss this a bit more later, they tend to follow each other. If there are already photons in that state, then there's the probability to go into that state is increased. But even without the presence of initial photons in that state, there's still a probability to go into the state.
So if we multiply NKR plus 1 with the transition probability that we find out for spontaneous emission, will it give us the stimulated emission probability?
So that would give you the total limit, because what we have is so the total probability is equal to NKR plus 1 times something. So if I put this something, if I put NKR as 0, then this is the probability for spontaneous emission. Okay, if NKR is 0, then the total probability is just the probability for spontaneous emission. So this factor here that we calculated is the probability for spontaneous emission. The total probability for emission is equal to NKR times that plus that factor. So what you could say is, you could say the total probability is the probability for the spontaneous emission plus the probability for the stimulated emission. So you can think of stimulated emission as proportional to NKR. It's, is that all right?
Yeah.
Any other questions? Okay. All right. So little announcement. Next week. So next week. Well, today we're finishing this quick and dirty quantum electrodynamics. We're going to get on to doing the more formal theory, and we're going to be applying it to high energy systems. But to do that, we're first going to step back a bit and do classical Lagrangian field theory. How to describe fields with classical Lagrangians and Hamiltonians. Sorry, how to describe classical fields with Lagrangians and Hamiltonians. Classical Lagrangian field theory. It's a straightforward extension of the Lagrangian theory that you already know, but applied to a continuous field. However, next week I'm not going to be here. I'm going on holiday. I'm going to the Bahamas. Get away from it all. Actually, I'm going to Canada. It's going to be freezing cold. I'm going to be giving 3 seminars to a research institute in Canada. So I'm going to be working and I'm going to be cold. But anyway, so who's going to teach you Lagrangian field theory? We have my superb graduate student, Indrajit Sen. Don't ask him about foundations of quantum mechanics because he has some funny ideas, but he knows his quantum field theory well. And so he's going to go through classical Lagrangian field theory, and when I come back the week after, we'll just review it a little bit. Something I should say. Sometimes you have to distinguish between tools that you need, things that you need to know about and be able to use, and knowing all the little nitty-gritty of how these tools are derived. For the purpose of this course, there are some basic results of Lagrangian field theory that you need to be able to use, and that's what we really need. Indrajit is going to explain here where they come from, and then should explain the background. But when I come back, I'm just going to summarize for you on one blackboard what you really need to know, the key results that you need to know that we're going to use to when we go on to quantize field theory. So some of the derivations Indrajit gives you seem a bit involved, you're not sure you follow all of it. Well, don't worry too much. It is the results that matter, the theorems, you need to be able to use them. Okay, it's a mathematical tool that we need to use. All right, so with that out of the way, we're going to do our last dalliance with the quick and dirty quantum electrodynamics is, so I mentioned, so far we've just looked at the dipole approximation for the interaction of an atom with the electromagnetic field. You might want to consider a system. It could be an atom, or it could be, let us say I have low energy charged particles, the kind of thing you've discussed in your quantum mechanics courses. Let us say I have charges E1, E2, E3, etc. And it is interacting with the electromagnetic field. Now, you're used to just if you're interested in, as I mentioned to you, there's something called non-relativistic QED, which in this course we're not all that interested in. It's used a lot in quantum optics. You've got low energy matter interacting with the electromagnetic field. It's an approximate theory. To give you, there's just one particular term that I want to get from the Hamiltonian. Without going through the details, those who are interested in the details, you can go through it. But the matter Hamiltonian, has a kinetic term. So we would sum over the different charges. It's just the momentum squared over twice the mass of the charge. This kinetic term, when you include the interaction with the vector potential, becomes the following. The momentum operator is replaced by, there we go, I may as well keep the C's, let's keep some C. When we go on to the high energy theory, all C's are going to be 1, H bar is going to be 1. Here we'll keep some H bars and C's just to be a bit closer to what you're used to. So there we go, we've got EI over C times AI squared, where this is AXT evaluated at the position. So here I have the positions of these different charges. So you may have seen this before when you describe the interaction. If you looked at the Schrödinger equation for a single particle in an external electromagnetic field, you will have seen this before, that the momentum operator gets replaced by P minus the charge over C times the vector potential. So the same thing works here, except here, this, instead of being an external classical electromagnetic field, it's the field operator. Sorry, I forgot to put the hat on. It's the field operator All right, so now without going through the formalities, if you're interested, look in the book. The upshot is that the total Hamiltonian can be expressed as the free Hamiltonian for matter. So you have terms of the form p squared over 2m plus the potential plus the free Hamiltonian for the electromagnetic field plus interaction terms. What do the interaction terms look like? If you square this and use the fact that we're working in the Coulomb gauge, what you find is you get the sum over I times minus EI over MIC AI dot PI plus EI squared over 2MI C squared AI squared. All right, now what happens? Let me just tell you about these different terms. So here is a term where we've got the quantized vector potential operator dotted with the momentum operator. These terms in A dot P. Let's think about terms in A dot P. Terms in A dot P, they are schematically linear in annihilation and creation operators. Okay, remember A has a plane wave expansion in terms of A and A dagger. So it's linear in annihilation and creation operators. Just like what we looked at before, we looked at the dipole, the electric dipole interaction, D dot E. E is minus the time derivative of A, but it's still linear. It's still linear in annihilation and creation operators. All right. So, in other words, you get similar effects. So what? The same effects as the dipole term. So, i.e., emission and absorption of single photons. Now, just to make clear that we understand what's happening, remember, probability per second is proportional to the square of the matrix element between the initial and final state. All right, remember Fermi's golden rule. There's this factor, there's a delta function, there's factor, but let's just look at the matrix element squared. There's the initial state, the final state, and the matrix element, where this is the interaction Hamiltonian. If this is linear in A and A dagger, then you see processes are possible. It implies that processes are possible such that one photon is emitted or absorbed. Because as we saw, for instance, if this state if it contains n photons. The annihilation operator can act so I get n minus 1 photons. And if the final state has n minus 1 photons, the inner product will be non-zero. I get a probability, because that's a probability for the number of photons to diminish. In other words, the atoms absorb the photon. The creation operator acts on the initial state, raises the number of photons. If the final state has 1 photon more than the initial state, the inner product will be non-zero. And so this term here, so this term corresponds to emission. Emission of a photon, absorption of a photon. Furthermore, if you calculate using the interaction Hamiltonian of this form, however, A dot P, for long wavelengths, the results reduce to those of minus d dot e, the electric dipole. So this is how you would actually derive the electric dipole approximation. You look at the coupling of matter to the electromagnetic field, you get these interaction terms. These terms here, when you calculate, in other words, you do the same calculations that we've been doing, emission and absorption of a single photon. If you do that calculation, you find that long wavelengths, the results are the same as if you had used this interaction here. So that's how you actually derive the electric dipole approximation. But now what we're more interested in is this new term. This new term. We've got the square of the vector potential operator. So this gives us some new effects, and let's just have a look. Let's have a look at what happens if I have what happens if my interaction term is proportional to a hat squared. So this describes photon scattering. Photon scattering. So I can have a photon coming in with a momentum k. It interacts with the atom or an electron or whatever is here, and it scatters off into another direction. So here, maybe let me draw some wiggly lines. We draw the wave vector. It scatters. In fact, I tell you what, let's just draw it like this. What I'm going to use later. So here's our atom at the origin. I have the wave vector coming in, and it scatters to a new wave vector through an angle theta. Now, why does it describe photon? Why does this describe photon scattering? All right, so, all right, I need to say that. Okay, or in fact, what's often called Thomson scattering. J.J. Thomson discovered the electron back in Cambridge at Trinity College, the greatest college in the entire universe. There we go. Thomson scattering in the entire history of the universe. So A hat squared has terms of the form A hat plus A hat dagger plus A hat dagger A hat plus A hat dagger. Now what happens, these terms are particularly interesting. What can happen is that you can annihilate one photon and create another photon. You imagine this term here acting on the initial state. It can annihilate the photon in one mode. Remember, these are, and I should say, these are of course sums. These can be over different modes. So let me write, let me leave off the polarization indices. Let me just put K, K prime, K, K prime, K, K prime. Maybe I'll put this the other way around. K prime and K. I'm going to write this out properly, but just schematically for the moment, imagine I have a term that's A, K, and A dagger K prime. What will happen? The annihilation operator can act on the initial state, remove a photon with wave vector K, and create a photon with wave vector K prime. So what can happen? Remember, as I mentioned to you in my preliminary sort of rough overview, you know, the way quantum field theory will describe this process is to say, well, there's initially the mode K is excited. Finally, the mode K prime is excited, and the mode K is no longer excited. So from the point of view of this heuristic particle language, we would say, well, the photon with wave vector K vanishes, and a photon with wave vector K prime is created. Okay? And mathematically, in the formalism, it comes from these annihilation and creation operators acting on the matrix elements in order to get a non-zero inner product between this state. If I take the initial state and I act on it with the interaction Hamiltonian, to get a non-zero inner product with the final state, if the final state has a photon in the mode K prime, and the initial state has a photon in mode K, this can be non-zero because of this term. This will remove the photon with wave vector K, and this will create a photon with wave vector K prime such that this is non-zero. Okay, so that's the idea, give you a sense of how this works. So now there's another wonderful homework problem for you, in which I'm going to go through, well, I'm going to sort of do it for you, but you check the details, okay? Homework, Thomson scattering. So what we're going to do is we're going to take, so a photon, instead of this being an atom, it's just going to be, I think we're just going to do, we can just think of it as a single electron. So it's just one electron, and we're going to take h bar omega, much smaller than the rest energy of the electron. Okay, so this is, so, you know, imagine you've got some long wavelength photon, low frequency photon, scattering off an electron. The energy of the photon is much smaller than the rest energy of the electron. And so what that means is there is no recoil. You can think, imagine the electron is in effect infinitely massive. It's just sitting there. The only effect of the electron is to scatter the photon. So in other words, the electron state does not change. The electron acts just as if it's just a scattering center, a charge sitting there at the origin. So what we're going to be interested in is the matrix element. The matrix element, so we're going to go from K prime, we have a book here, for some reason it starts using alpha and beta. All right, let me follow the book's notation so I don't get muddled. So this is the initial photon with wave vector k and polarization alpha. So we put an alpha here instead of r. So alpha is using alpha. So alpha is 1 or 2, and the final photon, or if you this heuristic, you see when people say scattered photon, it makes it sound as if you have this thing that exists. It comes in and it scatters. You know, but this whole language, from the point of view of quantum field theory, the initial excitation disappears, and that mode, the excitation of that mode vanishes, and a new mode is excited. So really, that photon has been, destroyed and a new one created. So the idea that a photon has been scattered is really nonsense. But anyway, the matrix element. And here's the final polarization, beta. So, your homework problem. First of all, we have to calculate this matrix element where the square of the. So remember, this is the interaction term that we found in the Hamiltonian by that trick, replacing momentum by P minus E over CA. We've got this quadratic term, it gives these new effects. The square of the, okay, we can do this. The square of the vector potential, so you're going to take the vector potential operator, the usual expansion in plane wave mode with A and A daggers, and you square it and you evaluate it at the origin. You should get the following. The sum over K1, so the book uses R and S, I'm going to use R1 and R2, which makes more sense to me. K1, K2, R1, R2, we have the following, H bar C squared over 2V, omega 1, omega 2, square rooted, epsilon, K1 R1 dot epsilon K2 R2 times, and here is where the interesting parts are. We have A K1 R1, there's an annihilation operator, e to the minus I omega 1t plus A hat dagger, K1 R1 e to the plus I omega 1 plus I omega 1t times, there's another term, A K2 R2 e to the minus I omega 2t plus A hat dagger K2 R2 e to the plus I omega 2t, where of course, where omega 1 is C, I'm putting in C's, it's the modulus of K1, omega 2 is C times the modulus of K2. You should be able to derive this expression straightforwardly, and from that expression, so there you have it, there you have your expression for A squared. So what you can now check, and I'll leave you to check it, check the following, you should find the following matrix element. k prime beta e squared over 2mc squared a hat squared 0t. What does this come out to be? So we've got one photon in the initial state. So there's just one photon in the initial state. There are no other photons. Okay, we've got an initial state with just one photon, a final state with just one photon. And but with two different, there are two different modes. So k and k prime. The matrix element comes out to be e squared h bar divided by 2mv square root of omega primed, where of course omega primed is c log k primed, of course, times epsilon k alpha dotted with epsilon k primed beta e to the I omega prime minus omega t. Okay, you can work that out. So now the transition probability per second for scattering into d omega. So we have k prime, have an angle theta, and let's think of the scattered photon as coming out restricted to a small range of solid angle. The transition probability per second for scattering into d omega is going to be W, and here I've got fixed initial and final polarizations, alpha and beta. So in the direction k primed, but with the solid angle element d omega, what is it going to be? It's going to be, you remember what we did before with Fermi's golden rule? We've got the square of the modulus squared of the matrix element. There's a 2 pi over h bar, there's a delta function, but we have to multiply by the number of states. The number of states in d3k, which is the number of states in d3k, which is v over 2 pi cubed d3k. Remember the same argument that we did before. So what does this thing look like? This thing here, let me write it down here, it's just like before. There's 2 pi, there's going to be an integral. There's v k prime squared dk prime d omega over 2 pi cubed. This factor is just this here. Remember that we have to sum over all the states in this little, we've got some little interval d3k in k space in order to get rid of the delta function. d3k is just 4 pi k squared dk, and so this is where this comes from, and it's exactly like before anyway, you go through it. There's the delta function h bar omega prime minus h bar omega, and of course we have the square, the modulus squared of our matrix element, and so we have e squared h bar over 2n v omega squared times epsilon. So these epsilons are real vectors, so the modulus squared is just the square. And what does this come out to be? It comes out to be if you work out that integral, and I'll need you to check. So the scattering probability per second into the solid angle element d omega comes out to be c over v e squared over 4 pi mc squared squared times epsilon k alpha dot epsilon k prime beta squared d omega, where energy conservation requires that mod k prime is equal to mod k. The incident and scattered frequencies are the same. Now, what we do, this quantity here is often called the classical electron radius for historical reasons. You may have met this before. This quantity in brackets, e squared over 4 pi mc squared, is just a convenient, so it's about 2.8 Fermi. Now, here comes some, I'm going to quote you something from the book. What do we do now? So the book says, dividing this transition probability per unit time by the, what it calls the incident photon flux, C over V. All right, the incident photon flux, C over V. I'm going to come back and talk about that. What you then obtain, so if you divide by the incident photon flux, C over V, you find the differential cross-section. The differential cross-section, D, sigma, alpha into beta, K primed, is equal to R0 squared, this classical electron radius squared, epsilon K alpha dot epsilon K prime beta squared d omega. And what is the interpretation of this? The interpretation of this is if you had a beam of, let's say, n incident photons, or some large number of incident photons, or if you imagine repeating this experiment over many times, where I've got lots of versions of the experiment, I've got lots of photons scattering off the electrons. Okay, there's a whole ensemble, if you like, if you can think of this as an ensemble. Or if I have a beam of independent photons scattering off a lot of independent electrons. Then what is this? So we've got the probability per second per unit time divided by the incident photon flux. This is the number scattered, the number of photons that are scattered into d omega per second divided by the number of photons incident per square centimeter per second. Now this number here is just n C over V. So imagine what we did is we took the transition probability per unit time, we divided by C over V. If I took the numerator and the denominator and I multiplied by n, then the probability per unit time times n would be the number of scattering events per unit time. Okay, probability times number of trials gives you the number of events. So yeah, you've met cross sections before, so you understand the idea of a cross section, differential cross section into a solid angle element, the omega. So it's the number of events that occur into the solid angle element, the omega per second, divided by the number of incident particles per square centimeter per second. Okay, now that is the usual language that is used. This is what all the books use. But what is this incident photon flux C over V? We've said in quantum field theory the photons are just excitations of field modes. There are no particles moving. What is it? The way this works, the way this is being described, they talk as if, remember we've got our volume V, we've got a large normalization volume V, and they talk as if there's one photon. There's one photon in the volume V. And if you repeated this many times, then of course this is times n. I've got n copies of this. And what the thought here, if you think about what is being said here, they are imagining that, well, I have a photon and it could be anywhere in this box. And let's take the probability to be uniform. And it is moving at the speed of light. So you imagine this volume V, if I imagine over a small time t, that this moves a distance c delta t. In other words, what you're imagining, you are imagining particles distributed randomly in the volume V and moving at the speed c. Okay, so I imagine I had a beam of photons that are distributed randomly in my volume V and they're moving at the speed c. Then it would be correct to say that, well, the incident photon flux is c over v, or multiplying by n for a whole beam. The number of photons incident per square centimeter. If I had n photons in here, distributed randomly, moving with the speed v, you can easily work out, well, how many photons per square centimeter per second will come through the area. It is equal to this. All right, now this is what I call BS. Now BS is a technical term and it stands for bad statements. Okay, this is, from the point of view of quantum field theory, this is nonsense. This is nonsense. Now, everyone presents it this way. I think, I've never actually seen this done properly, but I think if you want to do it properly, you'd have to think in terms of quantum field theory, in terms of the momentum coming in the initial state. So probably you could describe it in terms of momentum flow, initially and finally, and do it properly. But nobody ever does it this way. There is this heuristic language that is used where you imagine, well, as if there's a particle somewhere in here with a random position and moving at the speed c, and you think that you imagine that I have an incident flux of particles with this flux. It gives you the right answers. But from the point of view of quantum field theory, this is actually nonsense. We're going to see this same argument used later on. I suspect that there is a way to do it properly in quantum field theory. You probably just have to think in terms of momentum flow, but I've never seen anyone do this. Okay, so this is a sort of heuristic language that gives you the right answers. So you divide the transition probability per unit time by this incident photon flux, and you get the differential cross-section, which I'll leave it to you finally, once you've got this answer, you want to find the unpolarized differential cross-section. What you need to do is average. So we imagine that the initial beam is unpolarized. So we want to average over the initial polarization. We want to sum over the final polarization. And the way we do it, we're going to have to sum over, basically we're going to have to evaluate the following sum. The sum alpha is 1 to 2. The sum beta is 1 to 2 of epsilon alpha dot epsilon, so k alpha k prime beta squared, using the trick, the same trick as we used before, that we have this orthonormal basis. Epsilon 1, epsilon 2, and k forms an orthonormal basis. If you use that trick, you can show that this comes out to be a half 1 plus cos squared theta. Okay, so the trick is epsilon k1, epsilon k2, and k hat is k over mod k are an orthonormal basis. It's the same trick that we used before. You should be able to find this, and so what you find is that then d sigma, the scattering cross-section, the unpolarized scattering cross-section into an angle theta, is equal to a half r0 squared, that's our classical electron radius, times cos squared theta d omega. If you now integrate over omega, the total cross-section for Thomson scattering is the integral. Well, I have to just integrate over d omega. The omega is d cos theta d phi, but a 1 plus cos squared theta. Fairly straightforward. You find it is equal to 8 pi over 3 times r0 squared, which is about 6.65 times 10 to the minus 25 centimeters squared. That is the cross-section for Thomson scattering calculated by quantum field theory. And in fact, let me add you a homework problem from the book. In exercise 1.3, where you're asked to consider Thomson scattering for how it depends on polarization. Please do exercise 1.3. It's the last exercise at the end of chapter. So at the end of chapter 1, there were 3 or 4 exercises. The last one is please do that exercise. And there it is. We've calculated the total cross-section for the scattering of a photon by an electron at low energies. This is low energies, where the energy of the photon is much smaller than the mass energy of the electron. Later in the course, we're going to do it at high energies. Exciting stuff. All right, so are there any questions? Any questions about that? All right, please go through the details. Make sure you have it all straight, because these kinds of things will come up in the exam. So it's expected that you can do them. I'm here today and tomorrow. If anyone wants an office hour, I'm away next week. There you go.